Lecture. In the last lecture we had introduced power amplifiers and the classes of operation. We discussed today class B, then class AB somewhere in between, and class A power amplifiers. You recall that class B amplifier, class B power amplifier was a very simple circuit. For integrated circuits, very simple circuit, two transistors NPN and PNP with the bases tied together and connected to the source, and the load is connected from the two common emitters to ground. And essentially Q1 conducts during the positive half cycle, Q2 conducts during the negative half cycle, and if there was no VBE on, then the amplification would have been undistorted power amplification. However, because of VBE on, because of a minimum threshold voltage for the transistor to conduct, the characteristic is like this. The slope of the inclined portion is unity, that is Vi dV0 dVi is equal to 1, but for VBE on, that is this portion which is the dead band. And obviously what we will get if we have a sinusoidal input, like this, if we have a sinusoidal input, and if these lines are 0.7 and minus 0.7, if this is 0.7 and this is minus 0.7, we take VBE on as 0.7, and this is Vi, then V0 would start here and end here during the positive cycle. So it would be something like this, where the two curves are exactly parallel with a difference of 0.7 volt, and this would be the output V0, and on the negative cycle the conduction will start here and you will get a curve like this, which is also exactly parallel to the Vi curve, but with a difference of 0.7. Okay. And this is the region where there is no conduction, and therefore you get a distortion, and this, as I had told you, is the crossover distortion. Suppose now the input voltage is increased. Input voltage is like this. The amplitude is increased. Obviously the crossing with 0.7 shall occur earlier, and therefore the dead band, the width of the dead band shall decrease, and therefore crossover distortion decreases with increase of maximum input voltage. Okay, crossover distortion decreases. However, as you know, we cannot increase VIM indefinitely because of, again, distortion considerations. Okay. We cannot increase VIM indefinitely. We cannot increase it beyond VCC anyway. That is the limit. No, what is the limit? VCC minus VCE sat. That is the limit of the output voltage. Therefore, the input voltage cannot exceed VCC minus VCE sat plus 0.7. That is VB. Okay. So we have a limit on this. We cannot increase it indefinitely, and crossover distortion in such a complementary symmetry amplifier is a fact of life. Now this cannot be tolerated in sophisticated applications, and therefore we have to find a way to get over the crossover distortion. And the obvious solution is that if in this complementary symmetry circuit, if in this circuit the NPN transistor could be biased at 0.7, that is, if VBEQ was plus 0.7, then obviously this transistor shall never put a dead band. Similarly, if in the PNP transistor Q2, VEB2 could be put at plus 0.7, then this transistor will also not set its deadband. All right. Why is the deadband created? Because there is a threshold. This transistor does not conduct, it does not conduct before Vi reaches minus 0.7 volt. And therefore, if I could bias this at minus 0.7 volt and this at plus 0.7 volt, then there would have been no crossover distortion. And however, the operation no longer remains class B, because if you look at the load line, we are not biasing at this point, we will bias somewhere here, which means that the conduction angle we are trying to make exactly 180 degrees, that is half of the cycle, but the operating point now shifts from the cutoff point to somewhere into the active region, and therefore this operation is called class AB. Class AB operation is a modification of class B to take care of threshold conduction in the BJTs, to take care of crossover distortion. Now, how is this done? We obviously cannot use a large number of resistors in an integrated circuit. So, how it is done is to use more transistors. Okay? And the circuit, please draw with me, circuit is very simple and nevertheless at the cost of a few more transistors. Let us see what the circuit is. You have a plus VCC and the main transistors Q1 and Q2. From here it goes RL, and this is V0T. Then you have the PNP transistor Q2, and this goes to minus VCC. All right. What we want to do is to bias this transistor Q1 to plus 0.7 and this transistor Q2 to minus 0.7. Now, this is done by connecting two PNP transistors in diode connection from here to here. From here to here, we connect two PNP transistors in diode connection. So, what we do is we have a Q3 which is connected as a diode, and we have a Q4 which is also connected as a diode.
These NPN or PNP?
These are both NPN. Both NPN. And if somehow or other we can keep this diode, if somehow or other we can keep these two diodes at 0.7 volt, that is, if we can keep Q3 and Q4 in the active region, all right, then the drop from here to here would be plus 0.7, the drop from here to here would be plus 0.7, and that achieves what we want to achieve. Why? Because of symmetry of the two circuits, this point and this point, the two potentials would be equal. It is a voltage bridge. Because of symmetry, if Q3 and Q4 are identical transistors and Q1 and Q2 are identical transistors, okay, I am not saying Q1, Q2, Q3, Q4 are identical, I am not saying that. There is a difference. I will tell you what the difference is, and this is an intentional difference. Okay. So, if Q3 and Q4 can be kept at VBE or VCE equal to 0.7, our purpose is achieved. Now, we do not want to draw any current from here. We just want to set up a voltage 0.7 here, a voltage 0.7 here. So, the current is not important, but we do need a current. Now, how this current is obtained is, we can either use a resistor from plus VCC to here, then it would be VCC minus 1.4 divided by which R? We have to put a resistance here, okay? That will be the reference, but since we know a better technique, this resistance required maybe a large resistance which we cannot. So, we use a Current meter. Okay, that's it. So what we do is from here, from plus VCC, we take a transistor. Now obviously the current mirror shall have to be PNP. Okay. So this is what comes here. This is Q6 and this current is, let's say, oh, I'll do it later. And the other one, other transistor, the reference transistor is this one. This is also a PNP and we require a small resistance here R1 and this can go to minus VCC. The current here, which direction? Here, this direction or upward? Downward, because it's minus VCC. So this is the reference current, IREF. And the two bases have to be connected together and this has to be a diode connected transistor. Okay? So this is a current mirror. The sole purpose of this current mirror is to supply a current here to the two diode connected transistors. Not just that, you see, it also supplies a current to Q1, IB1. It also takes a current from Q2, IB2. This base current goes away. Agreed? Nevertheless, if the two betas are large, then we can ignore these two currents. And as you know, in a current mirror, this current would be approximately IREF. Okay, approximately IREF. So the current that passes through Q3 and Q4 shall be equal to, approximately equal to IREF each. Why approximately? Because we are ignoring IB1 and IB2. Okay, we are ignoring IB1 and we are ignoring IB2. So I sub C3 is approximately equal to I sub C4, approximately equal to IREF. Okay, I am explaining qualitatively. When I make a quantitative derivation, I will assume all of them to be different and you will see the reason. Now, the point that I was mentioning, tacitly I had assumed, I did not mention, not tacitly, I did not mention that Q1, Q2, Q3, Q4 are identical. I didn't mention this. Let's name this transistor also, Q5. The reason is the following, that these transistors Q3, Q4, Q5, Q6, they are not to supply large currents. Large currents are to be supplied only by Q1 and Q2, right? The sole purpose of Q3 and Q4 are to establish a threshold voltage, a cut-in voltage of 0.7. The sole purpose of Q5 and Q6 is to supply a reference current to Q3 and Q4. And therefore, since current levels are not important, these transistors can be made with much less junction area than these two transistors. Why much less? Because the larger the current in the circuit, larger the current drawn from the transistor, the more will be the dissipation and the more will be the junction area required to supply this current. Otherwise the transistor will burn off. Okay? So the emitter junction area for Q6, Q5, Q3, Q4 can be much less as compared to that of Q1 and Q2. Now what does this affect? Which parameter does this junction area affect? It does not affect VBE. The thresholding of a diode is independent of the junction area. What it affects is, if you remember, the saturation current I sub S. You remember the relationship I sub C equal to I sub S exponential VBE by VT. Agreed? It is this I sub S that is affected, the reverse saturation current, by the junction area. So, if the junction areas of Q6, Q3, Q4, Q5 is less than that of Q1 and Q2, IS3, IS4 would be less than IS1 and IS2. Okay? You might ask me, why create this complication? Because in an integrated circuit, every modified step of fabrication costs money. every modified step. If you have standardized these steps and make 1 million transistor and if you modify one step and make 10,000, maybe the cost will be comparable. Each modification costs money. You have to regulate the flow of gas, and this has to be automatic. Therefore, you have to break the process, readjust and run it again, and this costs money. Okay? And now, so therefore, why should we make the junction areas less? Yes.
So that current either going through Q6.
Yes.
Where does it flow through?
It flows to Q3, Q4, and this is Vi. I beg your pardon. I have not shown you Vi. This is Vi. So it flows like this, and in the path, while it flows, it gives out a small part IB1 because there is a bigger Q1 here. Okay, but it gets its price through IB2. Q2 gives some quantity back, and that's how it replenishes. But as I said, if beta 1 and beta 2 are large, then IB1 and IB2 can be ignored. Going back to that question, why should one have less junction area in Q3, Q4? Why not make them identical? That will unnecessarily increase the cost of the chip, because the junction area, the cost of an integrated circuit is determined by the number of steps, the time taken by steps, but primarily by the area of silicon that you have been using. And therefore, there are 4 transistors here. If you can reduce the junction area to 1/4, then this would be equivalent to fabricating 1 silicon transistor of a larger capacity. Agreed? So IS3 and IS4 would be approximately would be much smaller compared to Q1 and Q2, and a figure of 1:4. This is what people use in fabrication. Most of the op-amp circuits, if you if you open them up, you will see that the main transistors, the subsidiary transistors, which are not required to carry large currents, are approximately 1/4 junction area. This is the rule of thumb. You can go to less, but then there will be problems of voltage insulation strength and so on. So 4:4 is determined as a compromise. Okay. Now going to an analytical formulation of the whole problem. You see, what we want is that VBE3 plus VBE4 should be equal to VBE1 plus VBE2. That this is a balanced circuit is a different matter, but analytically we shall bring that balanced equation later. But analytically, our simple KVL is that VBE3 plus VBE4 is equal to VBE1 plus VBE2. Okay, let's write this equation. Then we shall be able to determine I sub C1 and I sub C2 requiescent values, because I sub C1 and I sub C2 are determined by VBE1 and VBE2. Okay, so the simple equation is that VBE3 plus VBE4 is equal to VBE1 plus VBE2. Let's write these VBEs in terms of the collector currents. Then obviously what we get is VT log I sub C3 divided by IS3. Alright. Is this equation clear? From that collector current equation. So plus VT log of I sub C4 divided by I sub S4 would be equal to VT. VT is the common factor. This Q by KT. I sub C1 divided by IS1 plus VT log of I sub C2 divided by IS2. And if I combine, you can see that IC3 IC4 divided by IS3 IS4 is equal to I sub C1 I sub C2 divided by IS1 IS2. Okay, very simple equation. You get rid of VTs, you get rid of the logs.
Is it IS1 equals to IS2?
Okay, I am coming to that. If you look at, because both of these transistors have to share the power, have to share the power. Q1 has to work during the positive half cycle, Q2 during the negative half cycle. There is no reason why these two transistors should not be identical. In fact, they have to be identical to have a symmetrical swing. The power supplies are identical, Q1 and Q2 have also to be identical, and therefore IS1 and IS2 are equal. As far as IC1 and IC2 are concerned, they should also be equal if we ignore IB1 and IB2. Agreed? If we ignore this. And therefore, our collector current I sub C1, which is equal to I sub C2, would be given by what? My equation would be IC1 square equal to IS1 IS2 divided by IS3 IS4 times IC3 IC4. Therefore, my equation would be IC1 equal to IC2 equal to square root of IS1 IS2 divided by IS3 IS4 multiplied by square root of IC3 and IC4. Well, they should also be identical, except for the fact that there is a base current also. So approximately they should also be identical, but let's put the approximation at a later point of time. We agree that IC3 and IC4 should be approximately equal. Now, as far as the transfer characteristic is concerned, let me go back to this circuit.
Excuse me?
Yeah.
So have we assumed that there is no current flowing through RL?
We are considering the DC conditions, therefore V sub I equal to 0 should give V0 equal to 0, and therefore no current. Is that clear? The question? Question is, once when we assume IC1 equal to IC2, these are DC conditions. There is no signal is applied. If Vi equal to 0, then V0 should be equal to 0, and therefore no current flows through this. So current must flow like this. Agreed. But I brought out this figure for a different reason. You see that if I go from ground via this path, if I go from ground via this path to ground again, we can write a KVL, and this KVL would be excuse me V0, I'm sorry, the KVL would be Vi plus VBE4 plus VBE3, that would be equal to VBE1 plus V0. Is that okay? From which, since the voltages are identical, you get Vi equal to V0 minus 0.7. Agreed? Similarly, if you go via the alternative path, excuse me, if you go like this, during the negative half cycles, Vi plus VEB2 would be equal to V0, and therefore once again V0 is Vi minus 0.7. Is the point clear?
Yes, sir.
In either cycle, this is the story. Okay. This was the same story earlier also, that created a dead band, but here it will not create a dead band. What I have is Vi equal to, no, I beg your pardon, V0 equal to Vi minus 0.7. Alright. Now if I draw the transfer characteristic, you see that when Vi equal to 0, V0 is minus 0.7. So the characteristic starts from here. When Vi equal to 0.7,
So isn't 0 equal to Vi plus 0.7?
that is correct. I made a mistake. It was the previous story. Previous story was Vi minus 0. Now it is Vi plus 0.7, and therefore when Vi equal to 0, V0 is this. Thus, the curve now, there is no dead band. The curve now, because we have shown that whether you go through Q1 or Q2, the relation is the same. So the curve now goes like this. Okay, there is no dead band. This is Vi and this is V0. Alright, the saturation, the maximum value, maximum positive value of V0, obviously, if you refer to this circuit, VCC minus VCE sat. So the maximum value is still VCC minus VCE sat, and it occurs at Vi equal to VCC minus VCE sat, yes, minus 0.7, agreed. And similarly, the minimum value that can be reached is minus VCC plus VEC sat, because for the second transistor, which is a PNP, it is VEC sat, which is equal to 0.2. Okay. So this is how you can find out what the input voltage is. This will be exactly the negative of this. Okay, for that particular input. Now you can now see that the swing is no longer symmetrical. Isn't that right? There is a slight offset here, but the point is we don't mind. We don't mind a little less swing, but what we want is that there should be no crossover distortion. So this is a very small price to pay, and in any case, no power amplifier should be driven to saturation. No power amplifier should be. So we won't go up to this limit anyway. If we are somewhere in between, then there is no problem. Okay, we should not go to saturation. What we should do is to see in the CRO that the output waveform is approximately the same as the input waveform. That is, there is no crossover distortion. Let's take an example. This operation is therefore called, it is neither class A nor class B, so it is called class AB operation. And class AB is specifically resorted to because of the problem of crossover distortion. What is the price that you pay? The price is that Q1 and Q2 are on the verge of conduction. Therefore, at the Q point, there is a collector current, and therefore there is an additional dissipation. On the other hand, if you had biased at the cutoff point, there would have been no DC quiescent current, and there would have been no dissipation in the absence of a signal. It is only in the presence of a signal that there will be dissipation, not otherwise. But in class AB, naturally, because you have to tolerate an amount of quiescent dissipation, the efficiency will go down. We will calculate efficiencies later, but let us look at an example. Suppose in this class AB circuit, suppose VCC plus VCC is plus 15 minus VCC is minus 15. Suppose VCC is 15 volt and R1 is 47K. R1 is that reference resistor for the current mirror. Okay, that current mirror I showed is a simple current mirror. It could be a Widler source. If you require much less current, it could be a Widler source. It could be a simple current mirror, or it could even be, if you can tolerate a large resistance, it could even be a single resistor. But large resistance is never used. Even if you use 20 transistors to avoid a large resistance, you do that, because the silicon area is much more cost effective in terms of multiple transistors rather than a single large resistance. Okay, I repeat this because these are the the main principles followed in IC fabrication, and followed for very important reasons. Important reason is saving money. Okay, make it as cheap as possible and sell it for as high a price as possible. Okay, that's the business technique. The question is to compute all quiescent currents, all Q point currents are needed, and it is given that Q1 and Q2 junction areas are 4 times the Q3 to Q6 junction areas. Okay, you are required to compute all the currents. The first thing you do is to compute the IREF. Oh, it is the second part of the question is, if beta NPN is 150, this is another thing I want to point out through this example, and beta PNP is 50. You might ask me, they are identical transistors made on the same chip, how come beta PNP is greater than beta NPN is greater than beta PN? This is also a fact of life, and that is why NPN transistors are preferred over PNP transistors. To get a high beta with a PNP transistor, one has to spend much more than one does in an NPN transistor. Even if made on the same chip, they are 1 to 2 times, 1 to 4. The spread in beta between PNP and NPN can be as large as 3 to 4. Okay, this is also a fact of life. When I say identical, you have to make special efforts to make them identical, in terms of AC parameters also. Okay, so but in this particular situation it doesn't matter. Why doesn't it matter? In this situation of a class AB amplifier, it doesn't matter, even class B, it doesn't matter whether beta PNP is 3 times less than beta NPN, because they are emitter followers. We are not asking for voltage amplification or current amplification. They are large signal amplifiers. All we want is that V0 should follow Vi. The power input does not have to deliver any power. All the power we shall extract from the power supply. Okay. So, under this condition, if this is true, can IB1 and IB2 be neglected? This is the second part of the question. It's a simple example, but it illustrates a number of points, and that's why I take this example. Now, if VCC, if you refer to the circuit back, we have to find out all these Q point currents. The first thing we find is IREF, alright, and IREF obviously is 15 VCC minus VCC, that is another 15, okay, this voltage minus this voltage minus 0.7, okay, minus 0.7 divided by R1 is given as 47K, and this calculates out as 623 microampere. If this is IREF, then obviously I sub C3 will contain, we will examine that point about IB1 and IB2 later, but I sub C3 is approximately equal to I sub C4, approximately equal to 623 microampere, both of them. Our point is to calculate I sub C1 and I sub C2, and that is square root of IS3, I beg your pardon, IS1, IS2, let me write it down, IS2 divided by IS3, IS4 multiplied by square root of IC3, IC4. And since the currents, the transistors Q1 and Q2 at 4 times the emitter junction area, this square root shall be simply equal to 4. Agreed? 4, and this would be 623 microampere, because we have assumed them to be equal, and this calculates out as 2.49 milliampere. The next point is whether IB1 and IB2 could have been ignored. We have ignored this in calculation, but end justifies the means. Let us see, if this is IC1, then IB1 is 2.49 milliampere divided by beta NPN, which is 150, and this comes out as 16.77 microampere. Compared to 623, obviously 16.77 can be ignored. Agree? Similarly, you calculate IB2, how much? 3 times this. That means 49.8 microampere. Even 50 microampere we could ignore compared to 623. Okay? 1:12 ratio we can. So, in practice, these approximations are indeed valid. Why? 50 microampere and 623, approximately 12. No, it's more than 12. More than 12? Yes, 5 times 12 is 60. So 62 must be more than 5, more than 12. Okay. The next point that we take up, we have considered class AB. We will come back to class B and class AB when we calculate efficiency. Okay, that means how much power is delivered to the load as compared to the power dissipated in the transistor. We would like zero power to be dissipated in the transistor. But you see, even in class B, the quiescent dissipation is 0. That is, when there is no signal, there is no dissipation. Actual class B. Suppose there is no crossover distortion, okay? It is not class AB, so at the quiescent point there is no dissipation. But when the signal flows, when the signal comes, one transistor produces only 1/2 of the sine wave. So there is an average current flowing in that transistor. Similarly, the other transistor also has an average current. And therefore, when there is signal, both transistors have a DC flowing through them, and that causes dissipation. That is the main reason for dissipation. Agreed? The other parts of the circuit, for example, the two Q3, Q4 in the class AB, Q3, Q4, Q5, Q6, they are not required to supply large currents. They are typically small current carrying transistors, and therefore the power dissipated in them, although they do it continuously, the power dissipated in them is of no concern. It is insignificant compared to the output transistors. So what we will do in calculating efficiency is power delivered to the load. Strict definition is power delivered to the load, AC power, and obviously not the peak power, it is the average power, which is RMS value of the voltage multiplied by RMS value of the current if the load is resistive. If the load is reactive, then we have to multiply by cosine of the angle between the two phasors. Okay, this is the average power dissipated in the load. That has to be divided. Strict definition is total power supplied by the battery. Therefore, if you have to put 2 meters at the plus VCC and minus VCC and measure the total. But we don't have to do that, because the current supplied to other transistors will be very little compared to the current supplied to the main output transistor. So we approximate this by power dissipated in the output transistors. The total power delivered by the battery is approximately equal to the total power dissipated by the output transistor, approximately. Okay, but that point later. What is so wrong about class A? Why not you say class A? Class A has been used for voltage amplifiers, for current amplifiers, for small signal amplification. Why not for power amplification? I have told you the reason. What is the reason? At the Q point, there is a dissipation. Even if there is no signal, the current flows, and therefore there is a dissipation, and that causes inefficiency. It could be, as you will see later, class A maximum efficiency is only 25%. Maximum. If you drive large enough voltages, large enough base currents, maximum that you can get. That is, for every watt that you deliver to the loudspeaker, you have to be prepared to dissipate 3 watts in the transistor, which is wasteful in terms of power, and elaborate cooling arrangements have to be. Okay, but suppose it is an intermediate stage. Suppose you don't require large power. It's a small power, basically, small power device. For example, an intermediate stage is an op-amp, in an op-amp, where a little bit of power is to be delivered to the next stage. Okay? Class A can be used. Not only that, if you are very fussy about music quality, even that avoidance of crossover by those transistors and all that may not be good enough. Then you have to go for class A, and you have to provide a cooling mechanism. You have to provide large fins, for example, for dissipating the heat. The quality, for quality music, nothing like undistorted class A amplification, even though the efficiency is less. However, there are ways of reducing the dissipation and all that. So basically, if it is a low power power amplifier, or a very high quality power amplifier in terms of audio quality, in terms of the frequency response, in terms of total harmonic distortion, THD, then class A is essential. And in class A, as I had said, the conduction angle is 360 degrees. That is, the transistor conducts for the total cycle, total input cycle. For an class A power amplifier, as far as the circuit is concerned, in the discrete circuit there is no difference. You have those R1, R2, exactly like a voltage amplifier. You have the RC, then you couple it to an RL and so on. But in a IC power amplifier, obviously we can't use so many resistors. We shall replace all of them by transistors, except for perhaps one, that is the current meter. No, RL is determined by your needs. RL is not integrated. RL is there will be an output terminal, you connect your RL, but that reference resistor is needed for the current. Okay. So what is done? The other thing is, in a voltage amplifier there is an RC as well as an RL. That is, usually we use a common emitter, but in a power amplifier, to reduce the number of resistors, we don't want resistors, we don't want voltage amplification, and therefore we can use an emitter follower. So class A is also in integrated circuits, not in ordinary circuits. In integrated circuit, the class A power amplifier is operated as an emitter follower. And I will draw this circuit and explain what is happening. The main transistor.
Excuse me?
Yes.
So in this case, will the two transistors be having VCE of 15 volts across them?
VCE of?
15 volts across them. So because it's 15 and 15,
30 volts.
So each one will have a 15 volts VCE. So can
each one will have 15 volts, yes.
Can they stand it?
They have to. You have to design such that they stand it, yes. If VCC is plus 15, in fact the transistor should be able to stand 30 volts. That's a very interesting point. I'm glad you raised the question. You see, in any IC design, you have to take account of short circuits, accidental short circuits. It may be done by lack of care, or it may be because of statics, charge accumulation and things like that. Okay, so if it is plus 15 and minus 15, each transistor VCBO, you understand what is VCBO? Collector based breakdown voltage. VCEO, collector emitter breakdown voltage, has to be greater than 30. Alright? Because there can be, the other transistor may be accidentally short. Then you have 30 volts across this transistor. And this may be short because of charge accumulation, for example. Alright? With a little bit of cooling or exposure, maybe the charge will disappear and then the transistor will come back in its original shape. Okay? Right. Now, about this circuit, and then I'll draw this circuit and then I'll say I'll quit for the next class. Class VCC, it is operated as an emitter follower, and therefore the load is from here to ground, RL, and normally you expect V sub I from here. the biasing of the transistor is done by a current mirror. That is, what I do is, now you no longer require a PNP current mirror. You can do it NPN. And if you can do it NPN, you should do it NPN. Alright? Because PNP has its own problems. So, we require a current mirror, a reference resistor R1, and this is Iref. Then you have this diode connected transistor. I am showing a simple current mirror. It could be a Widlar source also, depending on what amount of current you require. Now, this would go to another transistor, the main transistor. Where would this go, the collector? I want to bias this transistor, Q1, not to the base. That is correct. It would go to the emitter. And these two are connected. They may not be connected. There may be a Widlar. There may be Widlar resistance here, W, RW. Depending on what current you want to. This is the DC that flows. Where does this go? As an integrated circuit, I do have minus VCC, so I put it here. These transistors, I will call them Q2 and Q3. You see the biasing? I have used only one resistance, that is R1, which can be a small resistance. 30 minus 0.7 divided by R1 will be Iref, and Iref is approximately the current that I want in VCC. That's all that I want. And of course, this voltage will be, now it has to be, Q1 is to be prepared for a voltage of 30 volts across it, at least 30. It must be able to stand. We will analyze this circuit tomorrow.